Hello and welcome. My name is Raktim, and I am the extension school student, making this presentation for the final project of CSCI 250 Abstraction and Design course. So I have implemented a hierarchical clustering analysis algorithm in Java. So the background is clustering is an unsupervised way of organizing objects into groups where we don't know the number of groups we are going to find in advance. And what we end up doing is we find groups that are the members of which are similar to one another. And that's called a cluster, which is a collection of objects which is similar between them, but they are dissimilar to objects belonging to other clusters in the same space. And why are we clustering? So the data that we are using here is a biological data generated from microarray experiments where basically you have numeric observations of genes across various samples. So here are the samples that we have, and here are the genes. And we can cluster the genes, which is basically the rows, to measure the expression at multiple time points or different conditions across various patients or groups. And we cluster genes to figure out or get similar expression patterns that may lead us to similar functional activities of genes. And we can also cluster the samples or the columns where the expression levels of thousands of genes for each tumor sample may lead us to find biological relationship among groups of patients or different experiment conditions or different time points. The term similarity that I have been using so far basically is a metric that you use to define what similarity is. And here I have implemented quite a few similarity distance matrix here, and or similarity in similarity criteria here. I'm just going to use the example of Euclidean distance in this slide. So here again we have the data, and this is the formula, which is pretty straightforward to calculate the distance between 2 points. And here n is important. N is the number of dimensions in the data vector. For example, if you're clustering genes, then if you're clustering the genes, which is the rows, then for each gene the n is the number of samples that we have. And if you're clustering the number of genes, that is this dimension, then n for each sample is the number of genes we have. So now the similarity or the distance metric tells us how similar they are, but once we have one item and a cluster or two clusters, how do we link the clusters together? And for that we need to define what is called a linkage method between clusters. I mean, how do I join these two clusters, or how do I join these two clusters, and based on what criteria do I choose? And that is sort of explained by the linkage method that we use. So there are three linkage methods. One is the single linkage method, where the minimum of all pairwise distances between points in two clusters is used. They tend to produce long and loose chain of clusters. And then there's the complete linkage method, where the maximum of the pairwise distances between 2 points are used. So the farthest point here and farthest point here, that separates the two clusters will then be used to join the two clusters together. They tend to produce very, very tight clusters. And then this is the most stable and most reliable, according to my experience, is the average linkage method, where the average distance of all pairs of objects are used from one cluster to the rest of the clusters together. And then this is the method that is frequently used by biologists or computational biologists in the clustering scenario. What is hierarchical agglomerative clustering? It's just a rundown of the process where each data point exists in their own separate cluster, and then we keep merging the most similar pairs of data points or clusters together until we have one big cluster left, which is sort of the root of the tree. And this is called a bottom-up or agglomerative method, where at the very bottom you have all the individual data points, and at the very top you have the top of the pyramid, you have one cluster which sort of all other clusters gradually lead and merge to. And this is the logical flow. You calculate the similarity between all possible combinations of two profiles, and then you take the two most similar clusters and group them together to form one new cluster. And then you calculate the similarity between the new cluster and all the remaining clusters, and you keep doing this process until you have merged all your clusters into one big cluster. At the end, you see a binary tree-like structure, which is also called a dendrogram. And here is the root, sort of like this, and there are the leaves, or all the data points, and the height represents how close the items are, or how apart they are, or how similar or how dissimilar they are from one another. One thing I should mention, that leaf ordering in hierarchical clustering is also important, but I have left it out. I have not implemented that feature. The order of the leaves are completely arbitrary in my implementation. But if there are n possible data points, there are 2 to the power n minus 1 possible ways of ordering the leaves. And optimal ordering is a problem in its own, by its own complexity, and it's beyond the scope of this implementation. The distances that I have implemented are the distance metrics: Euclidean, Pearson correlation, cosine, dot product, covariance, Pearson uncentered, Pearson squared, and the linkage methods that are supported are single, complete, and average. Acknowledgements: Professor Gregory Morissette for a wonderful, wonderful course. Gregory, our extension school TF, was fantastic, and I got a lot of help from him over the emails, and very thankful to him. Victor for letting me sit through his day sections, and I'm very, very grateful for that. It was very helpful. And many, many thanks to the Piazza responders. The feedback there, the question answers, the back and forth was very informative and very resourceful. And finally, a big thanks to my project TF, Meng Xiaohei. He was fantastic with his inputs, with his advice, and his constant endeavor to check my progress. I mean, I'm being a slacker. I know how important that was to keep me on track and deliver the project on time. So thanks, Meng. Thanks a lot. So that's it for the presentation. I'll now switch to the demonstration part, where I already have the directories I need. So this is the directory structure. That the bin is for the class files. The data is where the data, the sample data file research. Report is, I'll come back to it. Scripts, I'll come back to it. Source is where all the Java files are. And there's this usage.pdf that I'm going to pack, which is this file, which basically tells you how to use the software and what are the parameters are and whatnot. I'll go through the steps here. So I'll start by compiling the source, and all right. So Java minus class path. I'm sorry, that's not the yeah. This is it. Java C. The output directory is bin directory, and the source is all the Java files in the source directory. Do that. That's compiled. Bin, yeah, that's there. Come back to a working directory. So now I'll try to show you the usage. Here we go. If you just do Java, the class path is bin, where all the class files are, and the main program name is main. If you just hit it without any parameters, it gives you the usage. There are two ways to use it. This is number one, where you give the program name, a data file, and you specify whether you want to cluster the genes or the samples, true and false, for samples and genes respectively. And it uses a default distance method and a default linkage method, and whether you want to do an absolute distance or not. So let's do that. Alright. So here I'm going to use the default parameters. I've said Java class path bin main. This is the data, in the data folder / whatever is the data file name, and cluster the samples. Okay, it did that. And what it does is, every time it runs, it creates a file in the scripts folder called for_r.txt. If there is one existing already, it overwrites it. And there is also a file called a show.r. It basically, it generates, the Java program generates this file in a way that you can read it into a statistical and graphical environment called R, which is very similar to MATLAB. You can load that in R and run the script. It will display the the results. So let me just show that R is running. So I have set the working directory to this. So this is the working directory. This slash the scripts directory. That's where the file is generated. And in that directory, there is also another file called as the show.r. So I'm going to just source that. And this is what it shows after my run. It uses the default average linkage, Pearson correlation, and here are the samples. Okay, I'm going to close this and come back here. And now I'm going to use the defaults again, but this time I'm going to cluster the genes. Alright, I'll go back to R, and it overrode the last file, and then I'll reload that program. And this is what it does. Now, since there are many more genes than samples, it's kind of on top of each other, but you can see the dendrogram at least. Again, at average, linkage, and Pearson correlation. Let me close this, come back. So I'm going to use some more parameters now. So let's go back and see what are the parameters available. You can always mention the distance name or a number, and a linkage name and a number. Let's try that. Okay, so I'm saying the same thing again. Class path bin main program data slash is the text file. Do the samples and use Euclidean distance and average and absolute distance of true. Alright, let me just go and load the file again. Alright, we got the samples dendrogram back. You can also do this with the numbers. You can just say, instead of Euclidean, so let's do the genes. Let's do the genes, and instead of, okay, actually, let's go back and check the parameters again. And so instead of sample, we're going to do the genes, Euclidean. Let's do a dot product, which is say 5, and let's do a complete linkage, which is 3. And absolute distance is, let's say, false. Alright, now you came back here, showed it. This kind of goofy kind of dot product complete linkage tree structure. So let me do it another way. So let's do that with, say, Euclidean 4 and average 2, and okay, so we get this. Oh, I'm sorry. Yeah, the average linkage and Euclidean distance. It looks like this. Some of the distance matrix may not make sense for certain types of data, so you have to keep that in mind. And choosing the distance metric is very important. It's as important as running the algorithm, so to keep that in mind. So I think that's all I had to show. So I'm more or less done. Again, the directory structure is like this. I'm going to clear the bin directory and the class files, and the rest I'm going to package. The report file is basically the report that I had to submit with the project. It describes a few other details if you want to read them. Scripts files I've already told you. Usage.pdf I'm going to include. Data files are in this data directory. So I'm going to package this directory up and submit as part of the presentation. One thing I forgot to mention while I was giving the presentation was why I chose Java instead of OCaml. And a simple answer is, I ran into some confidence problems. So I was doing very well, and I was all set to use OCaml for this, but until I hit infinite data structures, and I was short on time, and I didn't probably devote enough time that the topic deserved. And I thought the class was also, and the sections was also not very elaborate on covering that topic. It's a mind-bending, and it's a really deep concept, and I struggled with it. Partly, the timing was a problem for me. But at that point, I hit a sort of a confidence crisis, and I wasn't sure if that would be a wise idea to take on OCaml and this project and do it all by myself. So I fell back on Java, my safe bet, and went along with it. Good or bad, that's the way it was, and that's the whole story. So I'll stop there. Thank you very much. I enjoyed the course. I hope you like the project, and I'll end there. Thank you.